Здравствуйте.
Так, добрый день. Начинаем лекцию. Today I will start with a new family of codes, which are called BCH codes. So BCH is actually an abbreviation from the first letters of the names of their inventors. So the names are very difficult. It's Bose, I guess, or Bose, sorry. Bose, Ray Choudhury, and H is Hockwingham. I'm not sure that I'm writing all the name correctly, but something like that. So BCH codes correct a constant number of errors. They have a very large rate, so they are similar to Hamming codes, and actually Hamming code can be considered also as a code from this family. So in other words, they generalize Hamming codes, but I will speak about that later in more detail, of course. So the parameters, so the alphabet is binary. Actually, there are codes also for non-binary, but for simplicity, we'll consider the binary alphabet. And this is the first parameter. The second parameter, call it M, is a natural number. And the last parameter, call it S, is also a natural number. So each code from the family is defined by two natural numbers called M and S. And this will be linear codes over F2. And to define those codes, we need consider, as for the Wozencraft code, a field, call it F, a Galois field of 2 to the M elements. So we will consider this field and we will use addition and multiplication of that field. And it is well known that that field includes F2. That means that, of course, in that field, there are 0 and 1, and we know that 1 plus 1 is equal to 0 in that field, what means that it includes F2 as a subfield. In other words, the characteristic of this field is 2. And we will use this feature several times. Now, I can already describe what are the code words. So we will consider polynomials A of one variable whose coefficients are taken from the large field of 2 to the m elements, and whose degree is strictly less than n minus s. So s is the second parameter, and it is used here. Each such polynomial will be represented using its coefficients. And we will write now a polynomial assuming, say, that s is 0. But actually, as I said, a bunch of leading coefficients will be 0. And also, this is the first requirement to the polynomial. And the second requirement is more complicated. We will require that that polynomial takes only 0 as 1 in all the 2 to the m possible points. That is, a of x is in 0, 1 in small field f2 for all x in f. This, at first glance, this seems as a very strange requirement. So, of course, not every polynomial takes such values. For example, a polynomial x doesn't satisfy this property. However, we will show that there are many of them. And as code words, we will use the tables of such polynomials, tables of values of such polynomials. Because of this second condition, table of values consists only of zeros and ones. So our alphabet has 2 letters, as I said. So we obtain the following parameters. So the block length is 2 to the m because there are that many elements in the large field. The alphabet is binary. Now, what can we say about the distance? The set of code words here is a subset of the set of code words of the Reed-Solomon code. For Reed-Solomon, we have only the first requirement. And we know that each Reed-Solomon code, code words of Reed-Solomon code differ in at least s+1 positions, because the degree is n minus s minus 1 at most. So the number of positions where 2 words coincide is hence that much, n minus s minus 1. And so the distance, the minimum distance, is at least s+1. And the only remaining question is what can be said about the dimension of that code. How many how many such polynomials are there? And this is a very non-trivial question, and the remaining part of in the remaining time, I will explain how to compute it. First of all, so the problem is that this second condition, that a of x is 2, it belongs to F2, is expressed in terms of the values of our polynomial. And the first condition is expressed in terms of its coefficients. It is difficult to understand how they interplay. And I will start with the well-known thing that each polynomial is assumed that we consider polynomials of the maximal possible degree, n minus 1. So s is 0. Then we have one-to-one correspondence between polynomials and their values. To each polynomial of that degree, so now we assume the degree is, say, n minus 1, we can compute the values, and this mapping is one-to-one. For each possible values, there is a unique polynomial of that degree which takes that values. We will be interested in only where values are taken from 0 and 1 from F2. And so we have also one-to-one correspondence between such values and those polynomials which have such values. And this correspondence may be expressed in the other direction using Lagrange interpolation polynomial. So if we know the values of a polynomial, then we can compute its coefficients using the so-called Lagrange polynomials, P alpha of x. Alpha ranges over all possible 2 to the m field elements times the value of the polynomial in that point, where P alpha of x has the following property. It is 1 for x equal alpha, and it is 0 for all the remaining x. And for each alpha, we can construct such a polynomial of degree n minus 1. Now we have to understand what happens if we require that the degree of polynomial is strictly less than n minus 1. That means that what in terms of coefficient, in terms of the values, what does it mean that a n minus 1, a n minus 2, a n minus s equals to 0? So how to express this in terms of the values? Of a's values. And we will see that each such condition is actually a linear condition over the values. But actually it follows already from this formula, but we will be interested in the exact form of these linear equalities And we will consider, we will be interested in linear equalities over F2 and not over F, because in this way we can understand how these conditions reduce the dimension. So if we do not have these conditions, we know that we obtain this all possible 2 to the m code words. So all possible values are, all values are possible. And so the dimension becomes maximal possible, m. However, sorry, not m, but n. Let's call it n 2 to the m. Let's call it n because it's the block length. So the length of the table is n, and all tables are possible, so the dimension is n. And now we need to understand how these equalities reduce the dimension. And to this end, we will use that property that our field has characteristics 2. And that property allows to express the Lagrange polynomials in a very simple form. First of all, let's understand trivial thing. If we add two numbers in our, so A and B belong to the large field Fn. If we take A plus B squared, we obtain A squared plus B squared without the terms 2 times AB. And that because 2 is 1 plus 1 is 0 in our field. The same applies to A plus B to the 4. It is A to the 4 plus B to the 4 and so on. And that feature of our field simplifies everything. So in particular, as Lagrange polynomial, we can take the following polynomial of degree n minus 1. X minus alpha to the n minus 1 plus 1. So let's define P alpha by that formula, and let's verify that indeed has the property we need. Trivially, if we plug alpha for x, we obtain 0. We obtain 1. We obtain alpha minus alpha to the n minus 1 plus 1, which is 1. If we plug anything else, some beta in P alpha, which is different, we will obtain beta minus alpha to the n minus 1 plus 1. And beta minus alpha is non-zero. And we know actually that every non-zero element raised to the power of n minus 1 equals to 1. This is because our field has n minus 1 non-zero elements, and so the order of the multiplicative group should divide n minus 1, and so the order of L element is divides n minus 1. And so this is equal to 0 plus 1 to 1 plus 1, which is 0. So indeed, these polynomials can be used as Lagrange polynomial. The actual Lagrange polynomial is defined in the unique way. So these are our polynomials. This is a simple formula for them. Now we claim that this formula may be rewritten in the following way, that x minus alpha to the n minus 1 is actually x to the n minus 1 plus alpha x to the n minus 2 and so on, plus alpha to the n minus 2x plus alpha the n minus 1. In all the formulas, we can use plus instead of minus because in our field, this is the same. Addition and subtraction coincide. And this can be shown in two ways. Either we need to use the Newtonian binom and show that actually all the coefficients are odd, and we obtain this. But instead of that, we can actually just multiply the left-hand side and the right-hand side by x minus alpha and verify that we obtain the same thing. Multiply both sides by x minus alpha. So what do we obtain in the left-hand side? In the left-hand side, we obtain x minus alpha to the n. And recall that n is a power of 2. The right-hand side, using the well-known formula, boils down to x to the n minus alpha to the n. And so it turns out that this is the same. First of all, minus and plus is the same. So we can just change minus to plus. Maybe it's easy to understand. And now we will use these equalities. A plus b squared is equal to a squared plus b squared. If we square the second time, we obtain a to the 4 plus b to the 4. And so on. N is a power of 2. Squaring x plus alpha m times, we obtain x plus alpha to the n, and on the other hand, using this equality, we obtain the right-hand side. So this follows from these properties, which I have mentioned in the beginning. And so our lemma is proven. So now we can use a more simple formula, and it's more simple. Actually, maybe it's not more simple. It's not simpler than that. But the advantage of this formula is that here we see the coefficients of Lagrange polynomial in an explicit form. So the leading coefficient is 1. No, that's usual. And the next coefficient is alpha, and so on. The last coefficient is alpha to the plus 1 plus 1, which is either 1 or 0, depending on whether alpha is 0 or not. So using this expression, we now can understand what means our equalities about coefficients in terms of polynomial values. So what is an minus 1, which should be 0? An minus 1 is the coefficient, this one. If we add such polynomials with coefficients a of alpha, then we will obtain just the sum of a of alpha. So this is the sum of the all values of our polynomial. So the requirement that the first the leading coefficient is 0 means a linear inequality. Actually, this is linear equality over F2 because all A of alpha are assumed to be 0 and 1. And this equality reduces the dimension by 1. So reduces the dimension by 1. So without that inequality, other inequalities, the set of coordinates has dimension n, the maximal possible, because all tables are possible. But if we require that S an minus 1 is 1, we require one linear inequality over F2. And such inequality trivially reduces the dimension by 1. And so the dimension will be, K will be in that case, well, let's write here, so S and K. So if S is 1, that means that we require only that the leading coefficient is 0, then the dimension becomes n minus 1 and not n minus 1. So let's proceed to the next test. Assume that we also require that n minus 2 is 0. How this reduces the dimension? So an minus 2, as we see from the form of Lagrange polynomial, is equal to the sum of all the values times alpha. Alpha times A of alpha. Again, the summation is over all the field elements. This seems as one equation. However, it's one equation over F. And each element of F is actually represented by M bits, because our field F is actually an m-dimensional linear space over its subfield F2. So actually this one equality that the sum alpha times A of alpha is 0 means M linear equalities over F2. And we are interested only in linear equalities over F2 and not over F, because our space is n-dimensional linear space over F2. And so reduces not by 1 as Z1, but by M. And here we had that effect because here A of alpha multiplied just by ones. And here they are multiplied by alphas. And alpha are elements of the large field. So reduce dimension of the space by M and not by 1. So we obtain n minus 1 minus M if S is 2. Now, let's proceed to the next test. When S is 3, then we also require additionally that the third coefficient n minus 3 is 0. As we see from the formal Lagrange polynomial that means that the sum of alpha squared, A of alpha, is 0. And this actually is also represented by M equalities over F2. However, those equalities are linearly dependent with the previous ones. Moreover, they are just derivable from this one. Indeed, this equality means that the sum of alpha, A of alpha, is 0. Let's square this equality. Let's write it here. So let's square this equality. So it's 0. So we obtain certainly 0. But on the other hand, using our rules of squaring, these rules, we know that this is the same as the sum of alpha squared, A of alpha squared. And recall that A of alpha are taken from 0 and 1s. So this is the same. 0 squared is 0, 1 squared is 0. So this is the same as the sum of alpha squared, A of alpha. So actually, this equality implies this one. So they are dependent. And that means that for S equal to 3, we actually have the same dimension and not less. And the same phenomenon will happen for all odd values of S. So if we require that, say, A minus S is 0 and S is odd, this is the same as requiring that the sum of alpha to the S minus 1 A of alpha is 0. And this is the same as the sum of alpha S minus 1 over 2. Recall that we assume that S is odd. A of alpha. And this is A n minus S minus 1 over 2. So the equalities for that n A n minus S is 0 is the same equality as the similar equality for A n minus S minus 1 over 2. So we obtain that each other increase of S doesn't change the dimension. So we obtain here 2m for 5, for 4, the same for 5. And so we see that, so let's write here the minimal distance. The minimal distance is here 2, here 3, 4, 5, 6. So we see that actually for an even S and for the odd S, we obtain the same set of coordinates. So it's worth to use only either S is 1, which is not interesting, or the odd values, even values of S. Let's see. So for these are even or odd. Oh, we need. So for 2 and 3, we obtain the same distance. We obtain the same dimension, but the distance for 3 is larger. So it is worth, it doesn't matter actually. For this and this, the distance is this, for this is this, the dimension is the same. This is the same set of code words. So we will assume that S is either 2 or 4 or 1. And so we obtain or we can assume that it is equal to 1, 3, or 5. But if we assume that it is equal to 3, we should keep in mind that the distance is actually not S plus 1, but S plus 5. So let's recall, let's come back to the parameters. Now we know what are the parameters. The parameters are the following ones. 2 to the m as the block length. Assume, say that S is even. Then we will obtain 2 to the m minus 1 minus m times s. And here we obtain s plus 2. Not s plus 1, but s plus 2, because for the same code may be obtained if we increase s by 1, as we have seen from the table. And for s equal to 0, the picture is a little bit different. From s equal to 0, s equal to 0 means that s equal to 0, actually, it's not interesting. The only one code from the family is missing here, where s is 1, but it's not interesting code. I think it's even is not called BCH code. So we assume here that s is at least 2, s is even, and we obtain the following parameters. For example, we can consider the code when m is 3. We obtain 8, 8 minus 1 minus 3, and 4. 8, 8, 8, 4, 4. Code. This is an example of the BCH code for m is 3, m equal to 3, and s equal to 2. Окей. Ну вот про BCH я закончил. Есть какие-то вопросы?
Нет.
Может быть, там, где МС, надо еще пополам разделить?
Что-то я не слышу. Вы что-то говорите? Сейчас.
Слышите меня?
Что такое?
Алло?
Я сказала, что у меня нет вопросов, а Сергей говорит, у Сергея вопросы.
Ничего не слышу. Напишите в чате, что ли.
Хорошо.
Так, где тут чат вообще? Мы друг друга слышим, если что. Да, вы-то друг друга слышите, я почему-то вас не слышу. Не знаю, что тут произошло. Вроде все в порядке со звуком. Да, правильно, вы исправили. Спасибо. МС пополам, да. Надо. Действительно, это вы правильно исправили. Так, это не все еще. We will need to understand now why BCH generalize Hamming. So BCH and Hamming. So Hamming codes are more or less BCH codes where S is 2. So for S is 2, we obtain the code with the following parameters: 2 to the m minus 2 to the m, 2 to the m minus 1 minus m, and 4. So this is BCH. And recall that the Hamming code has parameters which are very close to that. 2 to the m minus 1, 2 to the m minus 1 minus m, but 3. So this is Hamming code. So what's the difference? The difference is that for Hamming code, the block length is 1 less, and also the minimum distance is 1 less. And let's see what's the difference between these codes. So for S equal to 2, BCH is defined using the following equalities: the sum of all the values 0 and the sum of all the values. So this is for BCH. Times alpha is also 0. If we write the parity check matrix of this system of inequality, we will obtain the following matrix. So the first equality means that we just sum up all the values. And the second equality means that we sum up all A of alpha with, this is actually M equations. And their matrix is obtained as following. In the first column, we have only zeros because for alpha is 0, everything vanishes. But for the remaining one, we just obtain, we have all possible different alphas, and that corresponds to all possible columns of height m. So non-zero. So columns 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. And so we obtain the following parity check matrix. But what have we for Hamming code? There, the matrix is just a submatrix of this one. We just list all possible non-zero vectors. One here. So the dimension is 1 less, 2 to the m minus 1. Here the dimension is 2 to the m. So actually you can see that we take all the Hamming, all the coordinates of Hamming code and just add 1 new bit, which is the parity of all the remaining bits. So the BCH for S equal to 2 is obtained from the Hamming code just by adding 1 bit to each code words, and that new bit is the sum modulo 2 of all the remaining bits. So in this way, we increase the block length by 1, and also we increase the minimum distance by 1. And so BCH is more for S2 is more or less the same as Hamming code. Actually, that code is also called the Hamming code of distance 4 when we add one new bit with the parity of all the remaining bits. Так, ну напишите в чат, понятно ли вот сравнение с Хеммингом. Потому что я почему-то вас не слышу. Ну, хорошо, понятно. Так. Так, ну давайте перерыв на 5 минут как раз. Так, Светлана, у вас почему-то не стоят оценки задачи 7,8. Ну что я говорю, это очень прислала. Сейчас я посмотрю. Кстати, попробуйте сказать что-нибудь. Мне кажется, я сейчас услышу.
Слышно?
Да, вот теперь слышу.
Хорошо.
Сейчас я посмотрю в
Здравствуйте.
почте.
А можно спросить про запись? Вот запись вчерашней лекции, она вторая половина побилась на Ютубе. С этим же ничего нельзя сделать, да?
Она даже не
Побилась? А что значит побилась? Ничего не
Там
слышно?
даже не вторая половина, там от лекции 20 минут.
Ну да, 20
Потом-
минут.
А потом тишина, и экран поплыл.
Я попробую еще раз загрузить. Я даже два варианта загружу. У меня там два варианта есть на компьютере.
Угу,
Так.
спасибо.
Угу. Так, сейчас со Светланой разбираться будем. Так. Значит, 6 ноября, да? На 30, 7 октября, 14 октября. Так, это вообще не то.
Само письмо 3 ноября было.
Я что-то смотрю, все периодически замощение у меня. Это, наверное, с другого адреса, что ли, посылаете?
Нет, все с одного.
Так, домашнее задание, коды с Сейчас. Значит, 3 ноября. Так, в проверенных у меня 3 ноября ничегошеньки нету. Так, посмотрим в непроверенных. Непроверенных. Светлана, ну все ясно, оно затерялось. Пошлите еще раз. Нет у
Шо?
меня, вот поэтому и не проверено, да.
Ну, у меня
Бывает.
просто видно письмо, но ладно, сейчас еще раз пришлю.
Ну, не знаю, вот куда оно могло деться. В спам, может быть. Да не, у вас 2 адреса. А, нет, 1. Так. In trash, in spam. Нет, да. Ну, бывает такое. Ничего не делаешь. Так, хорошо. Так.
Я еще раз отправила. Наверное, должно прийти будет.
Так, Светлана, скажите еще что-нибудь, чтобы я уверен был, что я слышу.
Я еще раз отправила задачи.
Очень хорошо. Это я потом проверю. Так, давайте продолжать лекцию. Значит, окей. Now I will explain you a very interesting paradigm, a new one, in the list decode, in the coding theory, which is called list decoding. And using list decoding, we will somehow improve the necessary conditions for existence of a codes. This is, so to say, byproduct of this paradigm, list decoding. So this paradigm was invented by Elias in 1950s. And the paradigm is the following one. When we consider decoding from errors, we want to recover the message exactly. In list decoding, we are allowed to output a small list of possible messages which contains the original message. So, in other words, here we have a message. We somehow encode it, obtaining a code word. Then that code word is transmitted to the channel, and some bits are changed, some symbols are changed. Then the decoding algorithm outputs X, and among other candidates for X, so it outputs a list of X's, X1, X2, and so on. X, call it X capital L, which should include the original X. But we do not know which of the X's is included. Which of the X's is our X that was transmitted. And this is called list decoding. So when, when L is 1, then that is the normal, the regular decoding from errors. When L is larger than 1, this is something new. And actually, we will, as usual, assume that the decoding procedure outputs the code word and not the message itself. So it should output a list of Y's such that that list contains the original Y. And again, we will limit the cheating capacity of the channel. We assume that the number of errors is at most certain known parameters E. And we will use the following we will call it EL list decodable. So the definition, so a code is E capital L list decodable if this is possible using that code, if there is such a D as on this a picture. So we transmit all the code, possible code words, and if the channel introduces at most E errors, we are able to recover that message using a list of size L. And it's easy to understand what does it mean in combinatorial terms. So the lemma states that a code is EL list decodable, EL is decodable if and only if every Hamming ball of radius L has at most of radius, sorry, E has at most L code words. Indeed, when we receive some Y, the procedure, of course, the algorithm D should output the list of all possible code words at Hamming distance at most E from Y. If there are at most L of them, then it will output the list at most L, and certainly it will include the original Y because it is at Hamming distance of E. And if there is some tilde Y for which the Hamming ball has more than L, say L plus 1 code words, then that tilde Y may appear as the output of the channel for all those possible code words, and so the algorithm D should output all them in the list, otherwise it is wrong. So in combinatorial terms, this list decodability means that every Hamming ball has small number of code words. And by the way, I forgot to say why that paradigm might be interesting. And the explanation is the following one. Sometimes we do not need to transmit an exact message. And this happens, for example, in the following scenario. Assume that we want to tell to our friend the solution to some equation. And we, X will be that solution. And the equation is known to our friend. He or she knows the equation, but doesn't know the solution. So we encode our solution, transmit it to the channel. The algorithm D will output a bunch of solutions. Not all of them are a bunch of candidates. Some of them is our solution. And we, on the receiving this access, we just can plug all of them into our equation and find out which is a solution. It might happen that several of them are solutions, but we do not care which solutions to obtain. So we can recover some solution, we can find some solution, maybe not that solution which was sent by our friends, but we do not care. We only need to have at least one solution. And usually this decoding is used in that scenario when we do not need to know, when we do not need, we need only to have a solution to something verifiable, which is verifiable. Good. Now we want to understand what are there some necessary and sufficient conditions for the values of parameters for which such a code exists. So we will now we will use the notation NK Q code, because the minimal distance is now not that important. So we have three parameters: block length, dimension, and the alphabet. And also we have two other parameters, E and L, for which the code is least decodable. Usually they, no, of course we can write like that, M, K, E, L, Q, if you like. But I actually haven't seen such notation. So anyway, we want to find necessary and sufficient conditions for existence of codes with such parameters. And it turns out that the volume bound, actually it's analog, provides both the necessary and sufficient conditions. So for least decoding, the picture is much better. More or less, we know for each parameters whether such a least decodable code exists or not. And let's state those necessary and sufficient conditions. So let's start with analog of the volume bound, or Hamming bound in other terminology. So volume bound is a sufficient condition, a necessary condition. It states that if EL least decodable and K Q code exists, then we have the volume of the ball of radius E times the number of coordinates Q to the K is at most L times Q to the N. So recall that the volume bound, just normal volume bound, not for this decoding, is this inequality without multiplying by L. So multiplying by L makes this inequality weaker, and for L1 is just the normal volume bound. So this is just the generalization of the normal volume bound for least decoding. And the proof is the following one. So consider all the code words and draw the Hamming balls of radius E with Z centers. Now they can't intersect actually, because we do not know we do not need the code to decode from E errors. So some string may belong to different balls. So we have two Q to the K balls which might intersect, but we know that each point belongs to at most L balls. And this is because our lemma. Recall that the code is decodable. PL, EL is decodable if every Hamming ball of radius E has at most L code words. Just reformulating that means that each point is covered by those balls at most L times. And that means that if we write all those balls, they cover the whole space of Q to the N element in at most L layers. So if we sum up the cardinalities of all such balls, which are actually the same, so we obtain the left-hand side, we count every point of the space at most L times. And so the sum of all cardinalities is at most L times the total number of points Q to the N. And so the volume bound is proved. Так, есть вопросы по volume bound?
Нет.
Ну, хорошо. And the next bound is the reverse statement, which is an analog, can be considered as an analog of the Gilbert bound. So let's be more precise. So volume, an analog of the volume bound. And now the analog, an analog of Gilbert bound. So in the analog of the Gilbert bound, we state a sufficient condition for existence of the code. And the sufficient condition will be this inequality, but without L. So stronger, a little bit stronger inequality. So if the volume of the ball of radius E times Q to the K is at most Q to the N without any L, then there is E, and L will be equal to small value, more precisely N log Q. N log Q, least decodable. NK code over the Q letter alphabet. So in the analog of the Gilbert bound, the size of the list is fixed. It's fixed by a small value. It's linear in N. So it's a small list. So our goal is actually to output a small list, and the list here is indeed small. So from a little bit larger, a little bit stronger condition than the necessary one, we can derive the existence of the code, least decodable code, for small list size. And this is proved using the randomized algorithm. So we randomized construction, so to say. We'll construct our set of code words, picking code words at random. So what does it mean? We pick independently Q to the K elements of our space. So we take Q to the K n letter words where each word is chosen at random with uniform distribution, and they are independent of each other. So pick them, choose them at random. Choose this thing at random. Okay, now we need to upper bound the probability that we do not obtain a PL decodable code. So we need to upper bound the probability that this bunch of Y's is not EL decodable. Now, what does it mean that it is not decodable? That means that there is a bad ball which contains more than L code words. So there is some Z, as the center of that ball, that contains more than L. That means at least L plus 1 code words. So that Z may be chosen in Q to the N ways. So we obtain Q to the N times the probability that that particular ball has more than L code words. So it has L plus 1 code words, and the number of those code words may be chosen in Q to the K, choose L plus 1, ways. So this is binomial coefficient. So q to the n is the number of ways to choose z, and this is the number of ways to choose these L+1 code words, y1, y2. Actually, they are numbers. So and now we need to multiply this by the probability that indeed all those code words fall into that ball. So what's the probability that one code word falls into the ball? This is the size of the ball, call it V, over the amount, the total amount of points, which is q to the n. So V over q to the n is the probability that some particular yi falls into the ball of volume V. And because we need L+1 code words, we need to raise this to the power of L+1. And that's because they are independent. By definition, all the code words are independent, and that means that their probabilities are multiplied. So this, again, q to the n is the number of ways to choose z. Q to the k, choose L+1 is the number of ways to choose L+1 code words inside that ball. And V over Q to the N to the L+1 is the probability that indeed all those L+1 code words fall into that ball. And now we just need to use to upper bound this. For binomial coefficient, we can use the following simple bound. A choose B is at most, what is it? This is A times A minus 1 and so on over B factorial. Here in the numerator, we have B factors, and each of them is at most A, so it is at most A to the B over B factorial. Very simple bound. So, and this will be chosen for this binomial coefficient. So we obtain at most q to the n, q to the k, q to the k raised to the power of L+1 over L+1 factorial. And actually for L+1 factorial, we need a simple lower bound, which is 2 to the L. So we have here L+1 factors, and each of them, except the first one is at least 2. So, and now the last term here is V to the Q to the N raised to the L+1. Now you see that by definition, so first of all, let's write it like that, Q to the N over 2 to the L, using this lower bound for this denominator. And here we group together all the terms raised to the power of L+1, which is Q to the K times V over Q to the N. And by assumption, Q to the K times V over Q to the N is at most 1. So this is our assumption that V times Q to the N over Q to the N is at most 1. So our probability is then upper bounded by Q to the N, 2 to the L. That actually one of these inequalities is strict, for example, this. Which one? Which one here is strict? I guess this one is strict. Okay. So at least one of them is strict. And so if we choose L equal to, if we choose 2 to the L equal to Q to the N, we will obtain 1 as a strict upper bound. And just taking the logarithm of that, we see that we need to choose L equal to log Q to the N, which means N log Q. So you see that our choice of L, indeed, we have chosen L as N log Q, and so we obtain indeed a least decodable code. Moreover, the theorem, as you see, is proved by a randomized construction. So if we require here this inequality to hold in a stronger form, say 100, for example, let's write here 100, then we see that a randomly chosen set of coordinates will provide a least decodable code with probability 99%. So least decodable codes may be constructed using a randomized procedure, assuming that the parameters satisfy a stronger inequality as in Gilbert-Baum. Ага, окей. Ну, на сегодня все. Сейчас я вам дам этот самый тест, и у вас 15 минут будет его сделать. Так, где у нас тест? Так, сейчас я стоп-шер сделаю уже. Так. Все, я кинул в чат. Вот смотрите, в чате появился тест. Значит, 14:35 заканчиваем писать. посмотрел я свою запись. Оказалось, что у меня Zoom действительно здесь напортачил. Сделал неправильный файл. И таким образом у меня правильного файла нет, поэтому его и в YouTube не может быть. Ну, остается вам просто эту лекцию прочитать в конспектах. Там, в общем, по-русски все написано, понятно. Там, значит, было... Ну, посмотрите, там я лог выкладываю. Там было про Рид Соломон плюс Адамар, декодирование вероятностное кода Адамара. Сейчас еще скажу, что там было. Рида Маллера кода. Сейчас я в чат это кину. Идем на чат.